Swayam Prabha. Digital India. Educated India.
So I'm extremely happy that these organizers invited me for this very special occasion, because in 1994 I joined IIT Kanpur and Shruti basically hired me, and the first day he invited me also at home for the lunch. And not only that, he had me just all through my career. He was my mentor, and I wish good health, Shruti. So with this, let me start. This is actually a laboratory studies of the reactions and chemical kinetics in a very conventional way. That this gas phase reduction of nitrogen dioxide to HONO by small hydroxycarbonyls. The specific hydroxycarbonyls that we used are the following. Should work. No. Okay, these two. That is a hydroxyacetone and a glycolaldehyde. Both of them are atmospherically significant molecules. Now, the reason for this study that this HONO, particularly this nitrous acid, it's an extremely important molecule. And the importance are the following, that it is a trace atmospherically significant gaseous species. Natural abundance is about 0.2 to 2.5 part per billion. And it is considered as this toxic atmospheric pollutant. HONO causes this mucous membrane damage. And at the same time, that this HONO, when it reacts with the secondary amines, is produced this nitrosamine, and which are considered to be the highly carcinogenic material. So there are many studies, I am just giving only one, that how these reactions of the nitrous acid with the many other organic molecules produces this harmful species, particularly from this environmental viewpoint. One more importance as far as the environment is considered is that this nitrous acid, that is HONO, once it absorbs light within this range about 290 to 400 nanometer, and which is basically abundant in the troposphere, it dissociates into OH radical and nitric oxide. So this is the gas phase absorption spectrum of nitric oxide. So it is seen that all this near UV region, it absorbs very strongly, and not only that it absorbs, this photochemical quantum yield is almost 1. The importance of this reaction is that this hydroxyl radical, which is known as this natural detergent of this atmosphere, because only mechanism that is available for this removal of carbon monoxide and methane from this atmosphere is the reactions with this hydroxyl radical. Now, almost all these model studies, it predicts that the contribution of this nitrous acid, that is HONO dissociation, to production of this daytime HO radical is almost 30% of these total abundances. Now, it is that not only this reaction is important from this outside, but there are many also the studies, indoor studies, that this unexpectedly high hydroxyl radical that is available in the indoors, that is also associated with this nitrous acid the dissociation reactions. Now, the problem to undertake the particular studies that I am going to tell here is that the abundances of this nitrous acid that has been measured in the pristine environment as well as at this urban atmosphere, these measured values are always larger compared to what are typically predicted by these atmospheric models. So the general conclusion is that there are many unaccounted sources in the atmosphere of this nitrous acid. So what could be the different sources? Many people are trying in different ways. So these are the common things that let me tell you, that this nitrogen dioxide reactions is the main source of the production of this gaseous nitrous oxide. In the gas phase, the reaction of the nitrogen dioxide and this water, it has been predicted that this almost reaction doesn't occur. Always the reaction occurs with the nitrogen dioxide with the water in the adsorbed state. And because of this Henry's law of dissociation constant, this nitrous acid, that is HONO, solubility in water is very small. So this comes always in the gas phase and nitric acid remains in this adsorbed state. But the situation is different. If you take this nitrite in the aqueous solution and acidify it, it produces again this HONO, but since its solubility is very small in the water, so it comes in the gas phase. There are other predictions that this nitrogen dioxide, it can absorb in the visible range. So excited nitrogen dioxide can react with water in the gas phase, but this reaction has not been conclusively established from the laboratory reaction or laboratory measurement. But this is very much accepted that this nitrogen dioxide mostly it reacts with the soil, particularly with these humic acids and on the soot to generate this HONO. And of course, there are the other reactions like nitric acid. It can be photodissociated to produce nitrogen dioxide. But in the gas phase, this reaction occurs only in the presence of this ammonia to produce this HONO and this ammonium nitrate. Then there are the photolysis of this orthonitrophenol that has been experimentally demonstrated. It was published in PCCP that this could be one of the sources. But what are the contribution to this atmospheric contribution, that is not known. So we explored that whether this different kind of alcohols or these aromatic alcohols and these aliphatic alcohols, whether it can contribute to this nitrous acid production in the gas phase. Because particularly the methanol, this is the second most abundant organic species in the atmosphere after methane. And although thermodynamically, this reaction appears to be favorable, that is, nitrogen dioxide can abstract one hydrogen atom from this methanol to produce nitrous acid. But all the laboratory measurement that have been performed by this different group, the reaction exclusively occurs in this channel. That is, methanol reacts with nitrogen dioxide to produce only nitric acid. No trace of nitrogen dioxide or there is nitrous acid. It has been found so far, although both the reactions thermodynamically appears to be this equally favorable. So this part is not known, this mechanistic details, why this reaction occurs only this channel, not this channel. We tried not only this methanol, but all types of alcohols, aliphatic alcohols, and alcohols containing many different kind of unsaturated group. But the reaction is always this channel. We did not find any trace of this nitrous acid production. We also tried different aromatic alcohols. Particularly, we were motivated by these theoretical studies, which was published in Journal of Physical Chemistry a couple of years ago. It says that the substituted phenol, substitution made from this chlorine atom OH group or this amine, that is phenols and that is disubstituted hydroxybenzene or this this aniline, it can possibly abstract this hydrogen atom from nitrogen dioxide to produce this HONO. So based on these theoretical studies, we tried, but this was the method, simple method. That is, within this infrared spectrometer, we put this reaction cell. It could be a linear cell or it could be a multiple cell. And at different temperatures, taking these different mixing ratios, different inert gas environment, we carry out this reaction. But we did not find even a trace of production of this HONO. Always, the product is either this nitric acid, a little bit of this nitric oxide, and this orthonitrophenol. That is the product that we identified experimentally. Although we also did this similar kind of calculations. Calculations predicts that HONO productions could be favorable, but reaction actually doesn't occur in that channel. So what we found that by varying this nitrogen dioxide concentration variation, that one of the prerequisites for the formation of this nitric acid is that nitrogen dioxide must dimerize to produce this N2O4, and this N2O4 is the main reactant species with these alcohols as well as with the phenol to produce these nitric acids. And then by varying this concentration and also time dependent studies that we established that basically reaction occurs in this 3:1 stoichiometry. Some kind of mechanisms also that we suggested, and at least with in terms of this calculation, it appears to be favorable. Very little activation energy is only about 0.6 kilocalorie per mole, so it's almost reaction, practically barrierless reaction. Although the reaction doesn't occur instantaneously, it takes a couple of minutes to complete the reaction. But the overall reaction is it appears to be a third order reaction, second order with respect to nitrogen dioxide, first order with respect to this phenol, and that fits well with this integrated form of this equation, third order kinetics. We also calculated that what is the rate constant value for this reaction. We published this report, published it in this journal. So this ACS Earth and Space Chemistry. Then of course in the course of our exploration, we find that although methanol doesn't react to produce this nitrous acid, but once you substitute one of the hydrogen atoms by either this formyl group or this acetyl group, what is called this glycolaldehyde or this hydroxyacetone, the reaction occurs exclusively this channel, that is nitrous acid production, HONO, and we did not find again a trace of nitric acid. So it means that if you just make this activate this one of the hydrogen atoms of this methanol, that although methanol or any other kind of this alcohol doesn't react, this reaction becomes favorable. Thermodynamic also this is favorable, but we could not carry out much of this electronic structure calculation here to establish that this reaction mechanism much. And this is the product spectrum that we show you experimentally. This is the reference spectrum of this HONO in the mid-infrared region. In that region, this is the spectrum of this nitrogen dioxide. Taking example of this glycolaldehyde here, and you see that all the lines, that is the product, it matches exactly with the reference spectrum of this HONO. So this gives conclusive evidence that this nitric oxide, this HONO production is the only reaction channel. We did not find any nitric acid production, and same thing is also true in the case of this when you take this hydroxyacetone. And these are of course these experimental evidences that with time, that how the reactant concentration depletes and this product HONO concentration grows. Now, just a little bit mechanism that we try to suggest, that this nitrogen dioxide, although that it can abstract this OH hydrogen, but once it abstracts it, instead of this production of this HONO, it appears that this nitric acid production channel would have been much more favorable. But on the other hand, somehow if it can abstract this hydrogen atom, then possibly that this is the some kind of DFT calculation. It shows the two-step mechanism. First step is some kind of barrier is there, is about 15 kilocalorie per mole, but the second step is the barrierless with some kind of intermediates. So whether this is truth or not, we do not know exactly. Then to establish the mechanism of this reaction, we faced a problem, because this hydroxyacetone and this glycolaldehyde, if you keep it within this reactor, then the surface deposition tendencies, particularly to get absorbed on the glass surface or quartz surface, it is so high that sometimes it competes with the rate of the reactions. In fact, at room temperature, surface deposition tendencies, that is getting absorbed on this glass surface, is much faster compared to these reactions. So these are some of these difficulties, but still, if we go to this higher temperature, particularly 50 degrees Celsius temperature, to somehow that this lower this surface adsorption probabilities, we are able to measure the reaction kinetics, and subtracting the surface deposition rate, that we are able to find that what should be the actual rate of the reactions. So kinetics of these reactions were established, and it was found that it was basically pseudo first order reactions with respect to reactions of any of this hydroxyacetone or glycolaldehyde. But this method, that is by increasing that for this pseudo first order, it is again this undergraduate the method that is everywhere used. We took nitrogen dioxide concentration at least 10 times more compared to these organic components, but the reverse was not possible because of the lower vapor pressures of this organic species. So we took a different kind of approach that is also used in the standard chemical kinetics to find that what is the order of the reactions with respect to this organic species. So it was found that this approximately the order, it is basically second order with respect to nitrogen dioxide, and first order with respect to this hydroxyacetone or glycolaldehyde. So overall reaction is the third order reactions. It matches of course well with this third order integrated form of this reaction kinetics data. And we just measured the same third order kinetics at these different temperatures to find out that what is this activation energies of this reaction. So from there, just we did some kind of back calculation that what should be the rate of the reaction at room temperature at this ambient atmospheric condition. So, and also that we tried to establish here that whether the reaction is truly a gas-phase reaction or it is a basically surface-mediated reaction. So, for that, this standard method that is used in this chemical kinetics by varying these surface to volume ratios, that we did that by taking cells of these different dimensions and the different shapes. But always we see that this it doesn't depend neither on the surface area nor on the shape of this the reaction cell. So we tried to say that this is a basically gas phase reaction. Referees, after a long debate at the PCCB journal, finally they accepted it. So this is how that we published it. So published in PCCB journal. And then that we tried to show that what is the basically rate of the reactions or how much it could be atmospherically significant, although the reaction channels are the different. But it appears that this reaction of nitrogen dioxide with this phenol, methanol, glycolaldehyde, hydroxyacetone and all these things, it all the cases follows the third order kinetics. And not only that, these reaction rates, the order is almost the same and except only these values. So in that way that we tried to say that this could be that one of the contributing channels to the daytime productions of this HONO in the gas phase. So that is what our contribution is this. And this is what just thank you very much. So this is our brief presentation on this topic.
Swayam Prabha, Digital India, Educated India.